Web of things. Most of the semantic models we discussed so far allows us to add metadata to make our data more interoperable. Now, once we start creating more interoperable data, we are interested in combining this data from other resources on the web, or resources coming from the other IoT sources. Sometimes this is referred to as a concept as Web of Things. Basically, we have a set of standards, a set of protocols, which allows us to communicate data. I don't know how much you're familiar with the low-level protocols like 6LoWPAN, or protocols which provide the IP over the wireless networks. Have you heard any of these protocols? Basically, there are different layers of the protocols which allow you to operate at the physical layer, network layer, application layer. I'm not going to talk about the protocols, but
I was introducing them to the protocols this morning, but actually we went very quickly on this kind of protocols.
Okay, if you briefly mentioned, yeah, I think that's. So generally, if you're writing applications, you're assuming you get your data, and often the access to the data nowadays is mainly through RESTful interfaces at the web level. That's why I use the terminology as web data. But probably then this morning you have briefly heard about these protocols. Like there are a range of protocols provide you basically connectivity within the networks, communication within the networks. Sometimes the protocols are similar to like IP networks. You just refer to a node, you get the data. Sometimes they are publish-subscribe based. This is like a co-op HTTP. Some of them are publish-subscribe based data. I don't know, have you heard about MQTT? MQTT is a protocol for publish-subscribe. If you're listening to a sensor providing data, for example, a temperature data, or I don't know, my body temperature data, you are interested when that data becomes available. Because sometimes this data is not a synchronous information, it's an asynchronous data, like depending on whether there is a change, whether there is an event, that data might become available. There are certain protocols. One of the most common protocols for that is called MQTT. If you're interested, you can just look it up. It's a protocol for sources to be able to publish, and consumers of that data can go and subscribe to that. I remember some of these early versions of like some of these messenger systems. I think Facebook, if I'm not mistaken, used to have MQTT based. Then you have your friends publish a message, then you get a notification because you have subscribed to listen to all the messages, for example, Paolo provides, but you don't know when actually that message is going to be available. You just you assume as a user you're interested, then you have subscribed to that. And when that message becomes available, you receive that message. That's how in different friends you have in different messenger systems that data becomes available. Once you have this infrastructure, you start communicating that data. Obviously, interoperability and providing semantic annotation becomes important. And now this is a design decision, whether you decide to add your data, your annotation on the source level, on the device level, or you decide to add your data on the gateway level, which stands between your network, between your sensors and your backend network, or you add your semantics in the backend. Each of them will have their own different advantages and disadvantages. If your data, as it's published on the source itself, has the semantics, then you have added more interoperability and it's easier to integrate that data. The problem starts when you have resource constraints, and if sending lots of information with overhead will consume more battery power, will consume lots of your bandwidth resources. If you start adding on the gateway, then the data goes in like unstructured formats, synthetic models, or some, let's say, comma-separated data goes to gateway, and you add the semantics on the gateway. Or you might even assume you just send the raw data with some structured syntax, and you add your semantics in the backend servers once you have processed that data. I'll show different examples of how you can do that, and often it depends on your application, depends on the resources and what you need to do with your data. But generally, most of the existing IoT solutions, as I mentioned, will use some sort of either XML or some synthetic data which limits their interoperability. And if we can add the semantics, we can create more structured information, which allows us to give that data to machines to process it. And let's remember the key concept behind the Internet of Things was creating machines can interact with each other and machines can start communicating with each other. And also providing automation, because once you have data structures which machines can read and interpret, your data becomes more accessible, and then you create automated processes. As soon as the data becomes available, they can integrate that data and can use it. However, the challenges are, we briefly discussed during the Q&A or the break, the semantic models, designing the semantic models which can be widely accepted sometimes is a challenging task, complexity of the semantics, and the real interoperability comes when you have different providers comply to your semantics. In terms of the technical solutions, we have different formats, the different models, different frameworks. I briefly mentioned like RDF, OWL. I didn't mention Sparkle. Sparkle is the query language for RDF data. When you write store RDF data, you can query them. In terms of ontology design, again, we discussed we need to identify the terms and concepts and define a common vocabulary and the relationships. Basically, an ontology consists of the common terms in a model, the relationship between those common terms and concepts, and creating a common vocabulary to represent those. And once we create a common language, a common model to represent the concepts. To make the solutions more adaptable, we need to create, obviously, tools for an ontology. It's not just creating a common language is not sufficient. We need to create tools to allow people to publish the data according to that format, to be able to link it to the other existing data, and try to avoid complexity as much as you can, because complex models, sometimes they look good on the paper, but in practical applications make it really difficult to process it and make your models lightweight. You heavily need to get people who actually are the domain experts, end users involved, to make sure that ontology is useful. And the value comes when you start linking different pieces of information to each other. And those different pieces of information could come from different sources, from different data sets. Some of them could be IT data, some of them could be existing data on the web. DBpedia was a good example, and how you can use existing data on the web to integrate it with other examples. It's called DBpedia. If I'm not mistaken, it's dbpedia.org. But double check. And there is a good one if you're interested in geographic information called GeoNames. There's an ontology for common landmarks, locations, and their properties. In DBpedia, you will find this already linked. These two vocabularies are linked to each other. Would you like to do some practice? Practically take a piece of paper and design an ontology and a walk around and we can discuss and try it? There you go. So we have two sensors. They both measure temperature. One measures ambient temperature, the room temperature. One measures body temperature. And we're assuming there are observational data types. One comes from a device, we call it device A, which has an ID. The other one comes from device B. Use a graph and show the model. If you wanted to represent that, what properties you would have taken. And how, we don't want to go into the RDF representation, but in terms of a graph, what that model would look like if you're designing an ontology. And quickly you can see the value. You already have two temperature data, and if you just use synthetic versions of temperature data, both they will very much look the same, right? But by adding some metadata, creating modeling primitives for that, you are telling machines this is ambient temperature, this is body temperature. And the way you're going to interpret them and you're going to use them is going to be completely different. In summer, I guess it gets here to 37, 38 degrees Celsius. It should do. If this room temperature is 37, becomes 38, should be all right. You might feel a little warm, but I think nothing serious probably happens. But if my body temperature is 38, that's quite dangerous. And then you need to tell the machines which is which. And that modeling will allow your machine to have the context of that data. Just use a simple graph and show what concepts you have, what relationships they need to have, and what you're going to call them, and create an instance of it. I'll pause this recording till we do this. Oh, Discord. Right. Sorry, my Windows crashed. That's very cool. Okay, it seems moving. You can represent now that data in XML format. You can write your XML and start creating, let's say, temperature, end of temperature, or you can use any JSON LD formats to represent that data and add semantics. And all we have discussed so far applies if you create, obviously, an ontology and you create JSON or JSON LD, you make it more compatible with maybe some of your legacy applications, and you can do that. Now, creating ontologies in practice, one of the important things is to agree on creating vocabularies. You need to find what are the common terms and find the common terms within that domain to be able to represent that. Sometimes that common term is the term you're representing a device, representing a concept. Sometimes you need also to find a common term to represent what you're actually extracting from your system. Let's say if you're doing a healthcare monitoring and you take lots of IoT data and you analyze it and you say this is infection, this is someone is ill, someone has fever, someone, I don't know, has cold, whatever you're analyzing it, those concepts you generate, if you're showing it to a user, if you're showing it to a doctor, that's a different thing. You might create a nice visualized dashboard, some information to be able to communicate that. But if you want to feed that to another application, to be able to use that, again, you need to think of the vocabularies because the different programs need to have a common term to be able to do that. Let's say if you have an application which analyzes people's body temperature, that their different body vital signals, and decides if someone has an infection, and you want to feed that to another software program which decides, for example, if I'm really ill, to call my doctor, send a notification to someone, call an ambulance, or do something, you want that piece of data, the information you extract, also become interoperable. For that, you need to think of what vocabularies, how you're going to use that. Like in healthcare, there are some well-defined vocabularies, terminologies. If you're interested in healthcare applications, check SNOMED, which represents some of the terminologies for medical applications as a common vocabulary for healthcare. Our example before the break on virology, like looking at gene data, virus data for different domains, you need to create a common vocabulary to be able to represent your concepts, to start actually connecting pieces of information together. Sometimes is that the sources you have, sometimes is the processed information. I'll show some examples what I mean by processed information. You should always look at efficient way of creating semantics. Is creating complex models could look good, but you need to start thinking of the end users of that application and create models which end users will be interested in using it. And sometimes creating fully semantic and completely automated systems might become very complex, or sometimes maybe you just you can combine that with some analytical models and do semi-data engineering, and part of it you use more intelligent information processing methods to be able to create really interesting applications. This is an example of a practical program we did a few years ago. We were trying to create a large search engine to be able to search for IoT data. The properties we took from IoT data was we were interested saying if the observation and measurements or the sensors we have, they have a data type, they have location data, they have time, and if I have lots of this information published, can I create a search engine that can search, for example, find me all the temperature data around this university campus, find me all the available IoT data in a region of location. A part of it is looking at the spatial data search. I don't know if you're familiar with looking for geographical data. You need to find your bounding box. You need to find what vicinity you are looking for the information. Sometimes it could be a really complex data processing because it's just having a GPS location and saying something nearby. It has lots of definition what nearby you mean. If I put a sensor here, nearby is 10 centimeters outside this wall, but there's a huge difference, the temperature data here and outside, and in terms of the processing is very different. In terms of what is, even in an open field, what is location, what is near to you, if you have all the GPS data, if you have done this processing, sometimes can be really complex. I'm not going to go into the detail of processing that information. Tomorrow I'll show some examples maybe. But we started, our initial approach was, we were representing all our data using RDF graphs. We had the location data using concepts or using GPS locations. We were adding type of data, of time. The problem with the semantics, as soon as you have, you scale up, your systems, especially processing large graphs, is very complex, and RDF triple stores and the data basically repositories which store RDF data, usually they are not very good at handling very large data sets. What we did, we started looking a little differently at the problem we had, and we did a bit of combination of data analytics and the design which helped us to solve the problem. We decided to keep the semantic descriptions at each network level. Means at each network level, we had the semantic, all the RDF descriptions, which we were storing on a gateway. Means on a gateway level, we had all the RDF descriptions, all the resource descriptions. From those, we started extracting some parameters which we needed to create our indexes. We took our location data, for example, and our type data. And from here, we were using some numerical models, some like analytical models, to be able to index the location data to create our indexes. Those didn't use semantics. We just took some parameters out of our semantics. What it helped us to do, we created a system which became largely scalable. There were lots of solutions we could use and apply to search for locations, search for types. And every time I find that data could be in one gateway, then I refer to that, and within that smaller scope, I did my semantic search. Instead of searching a very large semantic graph, you took a few parameters, you created indexes on those parameters. Paolo this morning also mentioned when they had problem, they took some parameters, some features out of their data, and they stored it in a relational database, and they did search. And once you find your data, then you drill down to your subset of the data set you have, and then you do semantic search within that scope. Again, that's something, a combination of an analytical model with some semantic model can help your application to scale up. In practice, we had RDF data at the lower level, at the level of our resources. Basically, all our resources, their properties were represented in a semantic model. We took some of those properties. We created an index level which worked based on those properties we wanted to index, and that was just a numerical model. If you're interested, tomorrow I will talk about it. We were using Gaussian mixture models to index, to create some clustering models. And then once we are basically indexing and discovery model worked, and once we identified probably the data I'm looking is probably in this network, within that network we could go and search in the RDF data. Then instead of having a very large graph, you basically break in your data to smaller subgraphs and you do your search in that graph. I'll talk more about this tomorrow, how we actually use the location data to create our Gaussian mixture models and create clusters and find a probabilistic model to be able to discover data. But the whole idea was if I have a GPS location, I want to find what are the sensory information I have available, what are the IoT data available within that geographical location. I could create a probabilistic model to search within my network, to narrow it down to a smaller network, and within network then do a semantic search to be able to find my data.
So in that model, the probability is related to the frequency of the data in that area, or
no? Probability is probability of you give a location, you give your GPS locations, and then you use a probabilistic model to say we use a Gaussian mixture model to create different clusters, and then put the data based on the location and type similarities within those clusters.
As created according to which dimension?
Similarity of the location of locations. And then when you are looking for a particular data, I say probably your data seems to be within this cluster, within this group. But it's a probabilistic measure. And that probabilistic measure will say 90% it seems to your data coming from this distribution. And then this is in cluster, for example, X, cluster I. And then we refer to that cluster, and within that cluster we start looking for, within our semantic description, for that type and that data. Our search was, you search for a location and search for a type. You say temperature within this location. And we're creating basically clusters which taking this to, basically it's not two-dimensional. We're taking GPS location, converting this to XYZ representation. Basically was a mapping. First we did a data mapping and we were adding type. Probably I'll talk more about it tomorrow. And then we're creating our clusters based on that. If you're familiar with GPS data or basically any longitude, latitude data, they are not numerical values, but they are representing angles. It means you cannot take two GPS locations and subtract them from each other, find the Euclidean distance. It doesn't work. I don't know how you tried it. Sometimes you come across people do that. I've seen a few times. It's not correct, because if you look at how longitudes and latitudes are represented, that was the worst way of drawing them. But they are basically angles. If you go towards the poles, they are coming very close to each other, but necessarily that distance is not the correct representative of where they are, or across the equator, how you're looking at it. Simply, you cannot take GPS location A and GPS location B and subtract them from each other and say how close they are or how far they are. You need to do some mappings. Like even Google Maps will use some sort of mapping to take a 3D space to basically present it in a 2D surface. Because GPS is a 3D, well, basically looking at a 3D.
There are several models to do this. There is
correct.
3D that they have, depending on the kind of coordinates that you have. There are several simple algorithms.
Yes, there are, exactly.
Are not the Euclidean plane.
That's correct. That's correct. Depending on your coordinate reference system and how you map your coordinate reference system to a 2D space, there are simple algorithms, but simply what I'm trying to say, you cannot take GPS and run like a k-means clustering to take GPS locations put in different clusters. You need first to do your mapping before applying any measure which uses Euclidean distance. And here we did the same thing. We took our GPS locations, we created, mapping is a very simple algorithm, but you need to first do your mapping before being able to process. And we added the type data, then based on that multi-dimensional data, now we created clusters, and a probabilistic model will say, if you're looking for data within this location, what is the probability of, in cluster 1, you find similar data sources from that. And you go through that. Up to that stage, there wasn't any semantics. Everything was extracted from the semantic features and was integrated into our indexes, into our hash basically data sets. Once you go to a subset, I say gateway 1 has your data. Within the gateway 1, we could do a complete semantic search, searching the graphs and find the exact data. That basically divided the scale of our RDF and graph search to much smaller graphs. Just some few other examples. I thought it could be interesting to see how people have approached to make the semantics more usable and more adaptable. This is a standard a few years ago came up called HyperCat, And their idea was in HyperCat, everything is a URI, similar to what most of the things we have discussed today. And their idea was, if you are referring to any IoT data, an IoT resource, if it has a URI, if it's like something like HTTP, whatever, add a cat to end of it. Doesn't matter what the URI is. And if that resource is HyperCat enabled, we'll give you the metadata description of that resource. Say, if I have a RESTful service which has a URI and I can read the temperature data from the shrew, if that resource is cat enabled, I can take that URI, add a cat to end of it, and we'll get all the semantic descriptions. Imagine if all the academic faculty members in this university, if they had a semantic description, I could take the name or URI which referred to their homepage, and I add a cat to end of it, you're assuming, and imagine if that resource was cat enabled, would have given me a semantic description of that. That was an engineering way of actually creating something which you can add semantics and also keep your system compatible with legacy systems. Because people could carry on as they were doing. They could just represent their data using URIs, using RESTful services, whatever they wanted. At the same time, there was just a convention, add a cat to end of it, and they get semantic descriptions. The early version of HyperCat didn't have ontological commitments. They were assuming you have just pairs of property value, similar to JSON. I think the follow-on generation has some ontological commitments. But again, you can see you can take a very simple approach and create some really interesting application. That's a very good way of representing semantics without changing your actually existing systems. A few years ago, my colleagues and I, we took the information on DBpedia, and we used the DBpedia information to allow us to collect the available IoT data and the sensors we're deploying with existing data on the web. For example, if I was deploying a sensor in Guildford in our university campus, that's where we are in Southeast England, I could go and find all the information related to Guildford, related to University of Surrey. For example, if you search on DBpedia University of Surrey, you will get the geo-coordinates. Automatically it's connected to geonames, will give you the geo-coordinates. You will find where it is. You can link it to other information. And we were using those information to allow people to give them more common vocabularies to tag their data. If you're publishing your sensor, to make that sensor widely acceptable, widely usable, instead of adding your tags, open tags, you can add them, but try to use some of the common vocabularies to be able to make your data more widely usable. The whole idea was, if you have a crowdsourced platform and people coming and adding their devices, their resources, allow them to connect to the existing sources, then you can follow on those links. Basically, you create hooks and you start following that to go and find all the interlinked information. And as soon as someone was saying, my sensor is in Guildford in this area, I could just simply link it to all other existing resources I had in that area and so on. And that individual or that person doesn't need to know about the others. You just create a platform which automatically starts putting pieces of information together and linking them. Someone could give you the air quality data, somebody else could give you the traffic data. Now you can put them together and you create really interesting applications, right? Someone can give you the parking information, somebody else will give you the traffic data or number of cars, and as soon as they start connecting on a higher level to similar concepts, you can use those information to be able to integrate data sources. The individual data providers probably even they won't notice it, but as soon as they use a common vocabulary, common linked data model, your data gets automatically connected. We created a model to be able to represent that data, to publish it, but I would say, if I'm too critical, I would say the biggest disadvantage is, again, this was designed for human users to test and try. It wasn't really took advantage of really automating it. Still, we relied on users to go and publish it, to be able to link it, to be able to search for it. A full automated of such a system becomes really interesting. You create a full automated system. I just take this, reads the GPS location, goes and finds on DBpedia whether there is a concept related to this, starts adding and linking it, and tries to find all the other linked information. If you can create that, something like that, then it becomes interesting. If you're looking for research ideas or things, then looking at if people start using different vocabularies, can you link their vocabularies to DBpedia? Can you link that vocabularies to other common ontologies, and then becomes more interesting. There's another notion in IoT which makes it a bit different from the web. If you like, let's say, I update my homepage maybe once a month. Most of the information hasn't changed for years. My name has always been the same. My phone number probably doesn't change. And all those information are static. And most of the semantic web technologies for the web are designed for relatively static data. You add metadata to your data, and that metadata more or less stays the same. In IoT, we are working with some more dynamic data. I'm not saying those properties change, but some of them actually changes. It's still the temperature you have read here. You have read from a sensor here 5 minutes ago. 5 minutes ago was 25 degrees Celsius. Will stay 25 degrees Celsius, but the accuracy of that sensor measured over time might change. The context of that environment might change over time. Your context of your application might change. And that adds a bit of difference the way you look at semantic web, semantic annotations on the web to semantic annotations on IoT. I would say most of the IoT semantics need to have some sort of notion of dynamicity. I just used, if you look at my university homepage, there's at the bottom of the page, there's a small logo of this. This is an ontology model called FOF, friend of a friend, FOF. This is one of the most commonly used probably ontologies, and most of the search engines, like common search engines, will be able to extract this information. What it does, this page will tell you who this person is, what is his phone number, email address, where he works. But as we discussed, they are not easy for machines to go and find those pieces of information unless you really program them and do some effort. But this FOF is structured information to say about a person, who that person knows, about the person's workplace, about the person's phone number. And if you create that structured information, you can then write search engines, you can write programs to go and find this person's email address. That's how sometimes like search engines can create little boxes to show people structured information about people. That's how you can go and extract information and feed it to another application. But why I added FOF here, two things. I wanted to say most of this information is static. Probably won't change unless I change my job. And one thing is also from that notion, and one thing is also this FOF has been very successful because it's very simple. It's just very basic, has very basic properties, and something which lots of information you have which can be represented like this, and quickly can be picked up by search engines, and this is something search engines are interested to find information about individuals. Then you search for someone's email address, they don't need to put too much effort to find it, just go and extract it from structured information. And when you look at the page, you don't see it, because metadata is designed for the machines, not for the computers. So, sorry, not for humans. Designed for the machines, for computers, not for humans, mainly. In terms of IoT, as I mentioned, there is a bit of dynamicity. For example, if you represent temperature data and you say at 12:30, whatever it was, 80%, I don't know, accuracy, and this was the value. Where is the value? Well, there is no value. I don't know, the location was here. Some of these properties might change over time. Now, whether you need to update that semantic description or you need to create different versions of that semantic description to link it, or if you are telling, I've measured, acidity of a soil using a sensor and the accuracy was 80%, and suddenly there was a flood and your sensor is semi-damaged and the accuracy has changed. Now, if you're updating that property, and always I'm referring to the same sensor, but basically the data I've collected yesterday had a different accuracy compared to the data I've collected today. You need to think of how that needs to be represented. You need to update it, you need to create different versions of it. This notion of dynamicity is very important. There are some standards in IoT or in semantic web can help you to provide that. One of the very well-known ones is a standard called PROVO, provenance ontology. If you search, there's a W3C recommendation for PROVO. I just said PROVO. There's a missing V. Provenance ontology, which allows you to represent the provenance of information. And that becomes very, very important if you're using the data you're collecting for a sensitive application. For example, in the UK, you don't probably have that problem here. Fracking oil is a big problem because I don't know. Do you know about fracking? They make very deep holes in the earth, and they put some radioactive material with some liquids goes under this and pushes the gas and oil up. Obviously, oil companies and gas companies, they have an interest. Their environmentalist groups are not very fan of this because they think that pollutes the environment. Now, most of the governments to allow to give license for pollution, for a fracking, what they do an environmental analysis. They will ask to collect some data, they will analyze that data, and they will integrate, probably they run, I don't know, some simulation models or how they analyze it, I really don't know the detail. But often that data, when it comes, what you're interested in is you're interested in the provenance of that data as well. Who collected that data? When that data was collected? What device was used? Because your analysis is very much biased and dependent on the sources and the basically provenance of that information. And that becomes a crucial part of your metadata in certain applications. If you're monitoring for a mission critical in an industry, I don't know, monitoring healthiness of a device, a very sensitive tool, you're collecting data, but you're interested in the provenance of that data, where it came from, or who said that, I don't know, the device is correct or not. Or if you're using crowdsourced information, again, profiling the sources of users you have and the provenance of that data becomes important. Then it's not just a piece of measurement, is what is basically the process chain that data has been collected. And often the data you receive in certain cases gets pre-processed, gets aggregated. For example, some of the platforms, they will collect very high resolution data, but what they provide as open data could be a different resolution of this. They might aggregate that data. That process chain which has changed, you need to also to represent what processes have been applied to that data before it gets to you. Again, provo ontology will allow you to represent that, then you can track your data back. That's something which the social media platforms, they don't have. Like when you see the fake news, you cannot trace it much back to see where it came from, what was the origin of that. If you had something like that, probably would have solved some of the problems for some of those information which verifying the source becomes a challenge. Another aspect is most of this data comes as continuous data. Most of the IoT data is just a series of measurements, like you just continuously measure. And what we call it are data streams. And if now you add a semantic to every single measurement you do, you can do that, but it's not very efficient. Then creating models which, let's say, each stream as a pipe, and it has the properties. The sensor continuously measures, let's say, every minute the temperature data here, and if that properties of that sensor doesn't change, instead of modeling for every single, adding all the properties of the sensor, accuracy, location, and all the information, maybe we just model it as a pipe, and all the information measurements coming back just are linked back to this. Again, we create a link data, say sensor A measured it. Then there are lots of modeling work in semantic modeling for IoT focusing on stream ontologies, stream data, and also streaming RDF. Because if you're publishing RDF data and if you're publishing streaming RDF, analyzing, querying that RDF data, it completely changes the way you work. Because initially, most of the semantic web technologies focused on static data. You store the data in a database, stay there for a while, you did the Sparkle queries, now you have streaming data which you're interested to extract some properties of that data and integrate it with other sources. Then that's a research area. There are lots of work. If you check International Semantic Web Conference, often you will find the state of the art work in RDF streaming and RDF stream processing. Another notion of using semantics, so far, most of the semantics we have discussed are created by us as human users. We do knowledge engineering, we create semantic models, we represent ontologies, we decide on vocabularies. But at the same time, the semantic themselves can actually be learned from by machines. I provide some examples. A few years ago, one of my colleagues and I, we had a PhD student who worked on using Twitter data for extracting traffic-related events. The idea was to use Twitter as a source of IoT data. And we used information around San Francisco Bay Area simply because we had highway police reports around the traffic incidents around that area, and they published their information in XML, which was easy for us to feed that data. That was the authority, like official incident reports, which you can take them and show them. I think on the map they are shown as the green ones. Yeah. This was a few years ago, I've forgotten. These are the like reports we get from official reports to say there is a traffic incident. Could be an accident, could be a roadblock, could be something like that. We were interested in saying if we can extract some information, people are reporting on Twitter. And if someone gets stuck in traffic, if they have time, probably they start tweeting and say this road is blocked. And by doing that, we're looking at the unstructured text on Twitter, simple text, there's some text processing, and looking at the location data. Sometimes we're trying also to extract the location of that incident from what people were tweeting and use that information to create now higher level semantics to say there is an event here. And that event itself is a traffic, is a roadblock. And there was a part of natural language processing and a thin layer of semantics on top, which just referred to certain events. And the rest was just the machine learning algorithms. And interestingly, for example, if you can just look at this picture, this is an incident report which is published by the police. And these are the Twitter information we have collected. And we added an impact to that, which saying number of people were talking about it. And often when there is an accident, people don't get just stuck on the same road. It could be an adjunct roads. Probably the traffic like stops the traffic in other roads as well. And what we're doing, we're trying to use the basically crowdsourced information to extract traffic-related events by the way people will publishing it. And that shows like the heat map of how people publish in this area. And these are the incidents we were getting from the traffic, and these are the official incidents are reported. And if you're seeing some of them are in the city because Twitter randomizes the location to keep the people's privacy. I guess they have changed it now more than this. But they do some randomization to make sure you can't just find an individual based on that. And of course, some of them ended up in the sea level. That was an example of creating semantics using text and learning the semantics on basically on a very simple level, the semantics of the events and saying what events happening. Then you can feed that to another application to use it for different purposes or different decision making. Here, if you see, the semantic layer is very thin. You just have an ontology of the events and incidents and their location. And the underlying, there are lots of raw data, lots of textual information which you analyze, but what you're interested in, just saying if there is an incident somewhere and what that incident is. And the rest is just learned by machines and fed that to an ontological model. Or in simple form, you create the very simple ontology and you don't have instances. The machines learn to create those instances and to generate that. That's a way of generating ontologies. A few years back, we worked on looking at the textual data and learning some topical ontologies. This is like, we downloaded something around like, I don't know, 20, 50,000 papers from ACM Digital Library. Most of them were on AI topic. We just did a search. We downloaded only the abstract page, not the papers themselves. And we wrote a program which went this sort of structured data, like a paper will have a title, you know the authors. We learned the format of the HTML page, which ACM was publishing that data. We started extracting this information and we fed it to a machine learning algorithm, which was learning the relationship between the topics. And was looking at, for example, always if ontology and semantic web appear together, they seem to be related topics. But whenever I see, let's say, ontology, I see semantic web. But when I see semantic web, I don't necessarily see ontology. And then we were learning hierarchy. What concept is basically a broader concepts, what concept is narrower concepts, and we were representing this as an ontology. Let's say the end product was, we gave 40,000 papers to machine, and we said these papers are related to AI. And our machine came up, or related to semantic web, and our machine came at that taxonomy. This was purely learned by a machine learning algorithm, completely unsupervised. Just looked at how the word co-occurred to each other and learned that. Let's say if you see Marco and I all the time at the same conference, you guess we work in the same area. If that conference is semantic web, you put us under semantic web. Now, sometimes you might see Marco in a conference and I'm not necessarily there, but that seems like always related to IoT. It seems like he's working on a more focused on IoT than me. And you start learning this. We looked at co-occurrences, the words. If you're interested, maybe tomorrow briefly I'll talk about it. We used latent derivative allocation and some Bayesian machine learning to learn this. But that's not important here. What I'm trying to say, these concepts have been used in textual to learning ontologies by looking at a large amount of data. A few years later, we started thinking, can we use the same concept to learn ontologies from events, from what was happening in the environment? And the idea was we had a set of offices, we had lots of sensors in them. And we started thinking these sensors are measuring, let's say, light, temperature, noise, electricity, and so on. We started analyzing this data, putting them together, and creating a set of concepts, saying, for example, by combining this, we created an algorithm to say there seemed to be a meeting in this room. The room seems to be empty. Yeah. Seems to be someone is talking on the phone. And so on. We created some concepts, right? There was just an analytical model and a set of rules which we applied to this streaming data. They were all IoT data sources, and we did some analysis, and we created a set of concepts. We could look at our sources of information and say what event was happening, right? Once we had this information, we started putting this over a month. And we started learning the patterns of activities. Like then my students could run a model and tell you, if today is Monday, if it's outside is sunny, probably I won't turn up in my office before 10 o'clock. Because they had looked at all the probabilities. They had learned what is the probability of being empty, around what time, what is the probability of moving from empty to like having a meeting, or whenever I talk on the phone, I probably after that I open the door and go and have a cup of tea. And then we could learn the model and we could develop the relationship of how those patterns and events were happening. Here you see, we were not interested in low-level semantics. All I discussed, we didn't have any of those. We were interested in extracting semantics of patterns and events and creating a model which gave us an understanding of the situation in that, an understanding of how those patterns are correlated, and what happens when an event happens and what follows after that. Again, this is a way of looking at semantics and extracting semantics, which now there's lots of research in it because there's lots of effort in understanding those patterns, relating those patterns to some activities in your domain, and then finding the transition between those activities, which if you put those pieces together, then you can create a really, really interesting now application of semantics. And here, most of your semantics are learned by the machines. Now you don't really design those basic levels and rely on lots of efforts. A few years later, we took the same concept and we applied it to our group of patients we were monitoring. We work with some of our colleagues, clinical colleagues, with supporting people with dementia, Alzheimer's. And one of the things we were trying to do was monitoring people in their home environment and trying to use the environmental data to be able to understand people's well-being. For example, if people's health start deteriorating, or the cognitive impairment increases, the pattern of activity might change. And we use the same concept. We started, we have like sensors, for example, that give us the, if you switch on, like here would be coffee in the UK, everyone drinks tea in the morning. If people start switching on their kettle to make a cup of tea, we have a sensor which tells us the kettle is on. And then we have movement sensors tell us where people go around the house. If you make a cup of tea and you go sit on a sofa, we have a pressure sensor which tells us you're sitting on a sofa. We use the same concepts to relate those activities to a set of concepts. And then we looked at how those concepts are related to each other, and we created a model of all the activities and the correlation between those activities. And we run our model for 2 months. And for 2 months, we learn all the patterning of activities in people. After 2 months, we leave our system, will work for another 2 weeks. We learn how much people deviate from their activities. Just think for a minute and see, do you do things routinely every day? I don't know how much people... Most of us probably, we have a sort of a routine. Or maybe over the weekend and weekdays our routine might change, but more or less we follow a routine, right? Not necessarily, but overall. Or even the amount of randomness in itself probably has a routine, like we have a level of randomness in our activity. What we're interested in is to identify if people start deviating from what is their norm. If people were active to a certain level for 2 months, you monitor and you learn that level of activity. If people make a cup of tea and go and sit on the sofa and hardly leave the house after that, you are interested in the level of surprise. And those are type of things you learn, not necessarily semantics in form of RDF and ontology, but you learn the semantics of the events, and you learn the semantics of how those events transition between different things. And now, if, let's say, you monitor Payan for 2 months, and he never, after he made his morning cup of tea, left the house, we started measuring the entropy. And I don't know if are you familiar with the concept of entropy? If not, leave it for tomorrow or Friday, I'll talk about it. And basically, it's the element of surprise. If our system comes across something which hasn't seen before, we'll be more surprised. If you do routine things, I will be less surprised. And that level of surprise, we use it as a measure over a day, and we're trying to identify if people's pattern of activities change. By doing that, if someone gets, for example, frail, becomes weaker, and their level of activity decreases, suddenly you start, your patterns will show, because the change in the activities and the transition between these activities will show itself. Or people become hyperactive, become agitated, nervous, and they walk around the house, you start finding those changes in the activities. Again, these are type of things which you can create a model, not necessarily OWL or RDF, but you learn the semantics of your environment and you can use them. And you can see how the steps of the work we did, I try also to tell you maybe a little of the story of how we moved from the model, looking at the analytical model, then trying to map our analytical models to some semantic concepts, and then trying to put it on an application, and then going back again, looking at how we can improve our algorithms. I'll talk more about actually how we use that activity detection and how we measure the entropy and what are the ways of actually analyzing that data. But overall, I wanted to say, my feeling is this, learning these concepts of semantics, learning from the environment, and then finding the correlation between different events in your environments, different data sources, can give you a really, really interesting view of the semantics of your environment, which you can use it for application. I think that there are lots of good research ideas and problems behind that to be worked on. Talk more about this. We need semantic models, but obviously we need to design for something which is fit for purpose. We don't want to design something which looks nice. We want to design something which can be used by different systems. And we need to think of who is going to use that data, who is interested in the semantics, what type of semantics we need, what are our interoperability requirements, and what are our design constraints. What are the available tools? What are the available vocabularies to be able to create something which can be used by the different stakeholders and increases the chance of basically our models or solutions we have developed to be taken by wider community and people who might benefit from that. Just a few other examples. A few years ago, well, a few years when I say 2015, my colleagues and I, we worked on an ontology model. We call it IoT Lite. That was a model mainly focused on observation and measurement data. We were interested in creating a very simplistic model, but with semantics, if you're measuring a sensory observation and measurement, you can link it to the provenance of that data, to provo ontology. You can represent the parameters of the measurements, like the quality of data, quality of the measurements, and the device that measures it. And we submitted to W3C because there now is a member submission on W3C's website. The link will be available on the slides. Last year, OGC, this is Open Geographical Consortium, and W3C, they had a joint effort. They published an updated version of, or a new version of SSN ontology, which now focuses on also providing observation and measurement data. That would be a different way, again, what we did in IoT Lite, to be able to annotate observation and measurement data, the data itself. If you remember when I said the earliest SSN, the first version only focused on the sensor as a device, this one also focused on providing the observation measurement data. And the core of it is an ontology called SOSA. Sensor, it stands for Sensor Observation, Sample and Actuator, SOSA. SOSA ontology. Again, the documentation is available. You can just go and look online. W3C has another interesting work, focuses on spatial data on the web. These are the location-dependent data, and come up with a set of best practices. If you're publishing location data on the web, these are the best practices. They're not necessarily any standard. It's just best practices. They say, if you publish your data this way, probably your data can become more useful and more adapted by other third-party applications and becomes more widely available. It's just I put it as an effort if someone is interested in this. Recently, my colleagues and I, we are working on creating sort of a search engine for IoT. Maybe I'll talk a little more about that tomorrow. And the idea is to be able to publish IoT data in a way which you can then use some properties of this, similar to the previous example of, I said, how we were indexing data. You create a search engine which you can search for the wider IoT data available from different sources. If you look at the current search engines, like take Google as an example, they're very good at searching for text, for terminologies, and searching for information available as web pages. Some extent also they are very good at searching social media, I don't know, data sets. But if there are lots of IoT data, numerical measurements, still they are not very effective in searching for numerical measurements, or the data becomes available for very good reasons. Because HTML is easier to access, crawler, because HTML uses hyperlink. You're probably all familiar with PageRank algorithm. PageRank uses the links between pages to be able to rank them. And IoT data is just probably as a URI, and you refer to that URI, get some value, and if they don't have semantic description, you don't have much about it. And that becomes a challenge. Then we have been working on some modeling aspect, and also looking at some other solutions which we can create something which we can index IoT data. I'll talk more about it tomorrow. In terms of designing ontologies, these are just some suggestions. When you design a semantic model, always think of a scale. And scalability is a big concern often for IoT applications. Creating something which works in small domains is good, but often what becomes interesting is your applications can scale up. Always think of who is going to use that semantics. It's not just we think this is a good model. It depends on the third parties are going to use that, or the application we are providing it. And that model should basically be useful for that purpose, or other purposes in future can come up. How that ontology can be can be updated and changed is important. Often we do the work without, sometimes in the past I've done it myself, without really documenting it. You need also to provide means to, in future, people can go and change it, update it, be able to use it to allow it to evolve over time. You need to provide some tools for validation. Again, I said in the healthcare applications, once we have the common language, we give it to the third parties to publish their information, but we have a validation tool. Before we integrate that data into our system, we validate it to make sure the data is consistent with what we have. Creating common vocabularies makes, we had this programming example, is if once we agree on common vocabularies, the possibilities, opportunities increases massively. And of course you can create good models, but it's better to use what is out there and try to link your data to the existing models. Some of the best practices will help you to make your data better adapted, more widely available. And you can see some of the very good and more successful examples are actually very simple ones, like friend of a friend ontology. One thing also is important is, so far, actually, I'm sorry I have to say that, but I've been talking for 3 hours, but we haven't solved any problem. We actually have made our problem more complex. We had just raw information. Now we have added lots of complexity to that data. We think it's good because we think we can integrate lots of data from different sources. We can link different parts of data to each other. But if your work stops here, then actually always be aware you might have enabled other people to do better applications. But so far, very much depends on how other people are going to use that data and how you're going to use your semantics. Then I always think when you're designing semantic models or any tools extract the semantics, try to think of the entire process chain to see how that information can be integrated and can be used. And obviously think of other tools, query methods, analytical models which are going to use that information, or provide some best practices, some examples how that data can be analyzed, can be processed to allow the other third parties to be able to use that. I finished 5 minutes early. Any questions?